So this question here, we're asked to visualize a situation. We've got a car that's traveling along and it hits a bug. So in the beginning, we have a car with some velocity. It's got an M, call it MC, mass for the car, and it's got some velocity. And there's a bug, let's say like this, falling along, and it's got a mass of the bug, MB, and its velocity equals 0. Well, the bug and the car, as they approach each other, they eventually collide. Like this. And so we're asked to determine, does the bug or the car experience a larger magnitude of acceleration? So which one experiences a bigger acceleration during the collision? All right, so acceleration, we'll go right to the definition. Acceleration is change in velocity over change in time. So we've got the acceleration of the car and the acceleration of the bug. And so if we imagine what's going to happen, let's say the car is moving at 40 miles an hour and it hits the bug, its velocity is not going to change very much. In fact, if you're in the car, you certainly won't notice it when you hit a bug driving down the road. So let's say its change in velocity is 0.001 miles per hour. The bug, however, is going to pick up and have like 39.999 miles per hour. And so what about the time? Well, the time that the bug hits the car and the car hits the bug are equal to each other. So the delta t's are equal. So in other words, the bug is going to, both of them change their speed over the same period of time, but the bug experiences a much greater change in velocity. Therefore, it experiences a much greater change in acceleration. So those are our bullets, and we can. That's the main concept there, with looking at it straight from a definition of acceleration point of view. So the bullets, we write them out. The collision. So we say acceleration is delta v over delta t. That's the first bullet. The second bullet is the delta t, the time of contact, is the same. One can't be in contact with the other longer than the other one's in contact with it. And we notice the car has a greater mass, so the velocity is changed less. So delta V is less. The second approach we could use to this is to use momentum. What we know from the law of conservation of momentum is the initial momentum of the system equals the final momentum of the system. And all the momentum in the beginning is the mass of the car and the velocity of the car. The bug doesn't have any. But afterward, we have the mass of the car times its new velocity and the mass of the bug with its new velocity. We know the change in momentum of the car is going to be equal and opposite to the change in momentum of the bug. So the change in momentum of the car is going to be mass of the car times the change in velocity of the car. And the change in momentum of the bug is going to be the mass of the bug times the change in velocity of the bug. Well, the mass of the car is large. The mass of the bug is small. So for these to work out, the velocity of the car must be small and the velocity of the bug must be big. So for example, if this is 6 and 2, large mass, small velocity, the bug would have to have it does have a small velocity or small mass, so it must have a large velocity. for those two to be equal and opposite to each other. And so this really truly gets at the why. The why the delta V is smaller is rooted over here. And so then we take those bullet points and we put them into nice, succinct prose.